Welcome to Mydreamsacademy.
Hello guys, welcome to Mydreamsacademy online tutorials. My name is Naji Benjamin Sunday, aka Masaka. Our topic today is electronic configuration. Please always remember to subscribe to our channels to get the latest edition of our program. Thank you. Alright, our topic is electronic configuration. Please, this electronic configuration will later lead us into a periodic table, but today we're going to study thoroughly electronic configuration. First of all, the word to configure means arrangement. Configure has to do with arrange. How do you arrange electrons in the atom? In fact, precisely, let's make it specific. Electronic configuration of atoms, because there are also electronic configuration of molecules. Okay. What is electronic configuration? Of course, the word configuration means distribution, arrangement. So electronic configuration of atom is the process of distributing electrons into the various orbitals, subshells, or shells available in the atom. Now, remember the words I mentioned there: orbitals, subshells, and shells. There are different words. An orbital is a region in space above the nucleus or around the nucleus where the probability of locating an electron is the highest. So a collection of orbitals, the actual seat, the particular place you are likely to get an electron at a particular point in time is the orbital. Okay? So now that is the actual seat of electron in the atom anyway. So a collection of orbitals available within a given space we give rise to either shell or subshells. Okay? Now, there are, look at this place. There are rules guiding electronic configuration. One is that every orbital accepts a maximum of 2 electrons. The maximum number of electrons that can be accommodated by an orbital is 2. Okay? Now, that is one rule. 2 is that the maximum number of electrons that can be accommodated by a subshell is given by this formula 2 bracket 2L plus 1. 2 bracket 2L plus 1. Okay? That is the formula. Now, of course these two here represent the number of electrons an orbital can accommodate. 2L plus 1 is the number of orbitals present in a subshell. Now, in the periodic table, there are 4 subshells. There are 4 subshells existing in the modern periodic table we are using today. What are the 4 subshells? S, P, D, and F. Please, you represent them with small letters. All these symbols you see here are derived from spectral terms. The S represent the spectral meaning of S is sharp. P is principal. Look at the principal I mean. That is meaning of this P, the spectral notation. D means diffuse. Okay, and F is fundamental. Now, all these subshells, S, P, D, F, I didn't say orbital because the orbit is different. Now, all of them has each of them is characterized by a number called azimuthal quantum number. For example, the azimuthal quantum number, which is this symbol L here, small l, not capital L, small l. The azimuthal quantum number of S, or the L value of S, is 0. This one is 1, this one is 2, this one is 3. Okay, so now the notation for electronic configuration is any L raised to power x. This L is the azimuthal quantum number, as you can see. X is number of electrons occupying this, where the whole of this is a subshell. Let me help you here to understand this more. There are 7 shells existing in a periodic table, in the modern periodic table. They are K, L, M, N, O, P, and Q. The principal quantum numbers for each of these shells include 1, 2, 3, 4, 5, 6, and 7. So this N you are seeing here will represent the shell. So if I write something like, for example, now if I write 3D, what this means is subshell. And this 3D is a subshell of M shell. A subshell of M shell. That is a smaller unit of a part of this M shell, not the whole of it. Because there are other available spaces within the M region, the M shell. Because you can still have 3P. Okay? So if you collect all of them together, you have 3P, you also have 3P, 3D, 3P, 3D, 3S. If you collect this together, all of this in together, you have the shell. These are the 3 subshells that make up this M shell. Okay? Now, that is on that. Then the next one is that, like I told you before, the first rule governing electronic configuration is that every orbital accommodates a maximum of 2 electrons. Another rule is that each subshell, every subshell accommodates a maximum electron which is equal to 2 bracket 2L plus 1. So the maximum number of electrons a subshell can accommodate is 2 bracket 2L plus 1, where the L is the azimuthal quantum number of that subshell. For example, if I want to know the maximum number of electrons P sub S subshell can accommodate, that means from this formula 2L plus 1, I'll substitute the value of L as 0 because the L value for S is 0. I'll put 0 here. Of course, 2 times 0 is 0. 0 plus 1 is 1. And 1 times is 2. It means the maximum number of electrons S subshell can accommodate is 2. Now, if I want to know the maximum number of electrons P subshell can accommodate, I'll substitute L value of P as 1. If I put 1 here, 2 times 1 is 1. 1 plus 2 will give you 3. And 3 times 2 is 6. It means that the maximum number of electrons P subshell can accommodate is what? 6. Then, similarly, the maximum number of electrons this subshell can accommodate can be obtained by putting the L value of D, which is putting 2, which is the L value of D, into this equation. If I put 2 here, 2 times 2 is 4. And 4 times 1 is, 2 times 2 is 4, and 4 plus 1 is 5. 5 times 2 is 10. So it means the maximum number of electrons this subshell can accommodate is 10. Take note of that. Then the third rule governing electronic configuration is that the number of orbitals present in every shell is N squared. Take note of this. That means that, for example, if I want to know the number of orbitals in M shell, I will substitute N as 3. So it means there are 9 orbitals in M shell. Okay? So there are 9 orbitals in M shell. Remember, this orbital was introduced by the quantum number called magnetic quantum number. Of course, magnetic quantum number divides shells into orbitals. Orbitals is the smallest unit. Alright. So if I want to know the number of orbitals in any shell now, I will substitute 4 here, which is 16. 4 squared is 16. So now, the maximum number of electrons a shell can accommodate class will be given by this formula. The reason is that every orbital accommodates a maximum of 2 electrons, and there are any square number of orbitals. So number of orbitals multiplied by the number of electrons which an orbital can accommodate will give you total number of electrons a shell can accommodate, which is 2n squared. So if I want to know the number of electrons that M shell can accommodate, the maximum number of electrons M shell can accommodate, in M shell I have 9 orbitals. So 9, and each of these 9 orbitals accommodate 2 electrons, which means 2 times 3, so 2 times 9 is what? 18. So it means the maximum number of electron M shell can accommodate is what? 9. Sorry, 18. And also in any shell you have 16 orbitals. So the maximum number of electrons any shell can accommodate is 16 times 2, which is 32. Okay? So now we proceed. We proceed further. In electronic configuration, there are rules. Sorry, there are standard rules that we use. Okay? Or a kind of laws that we use. One is what we call the construction principle or the building up principle. Building up principle, which is simply the word. We normally see this word Aufbau principle. This word means this or this. It's a German word. Okay, so there is a principle, and this principle is based on N plus L value. Sum of this N plus L. Remember, the symbol for electronic configuration, the notation is N raised power x. Remember, the x represents number of electrons occupying the subshell NL. Okay, so if you sum the N, if you add N value to L value, you get the total energy of a subshell. So electrons, the subshells in the atom, like I told you, you can decide to fill electron into orbitals. You can write electronic configuration by filling electrons into orbitals, or filling electrons into subshells, or even shells. But the most acceptable one, the most convenient and most acceptable is electrons filled into subshells. Okay? Hey. Because that of orbital is complex. Now, that of shell doesn't actually give the two representation of the atom in the periodic table. So we prefer the one done with subshell, right? So now, this very subshell, you use this N plus L value, energy value, to fill the electron into subshell. Now, let me show you this. I may have 2p, I may have 3s, I may have 3d, I have 4s. These are subshells. 2p subshell, based on this principle here, please, NL. You can see the value of N is 2. And remember the L value, the L here, remember S is the L values, S is 0, P is 1, D is 2, and F is 3. These are the L values of these orbitals. Sorry, subshells, not orbitals. Okay? So now, for this 2p now, it means the value of N is 2. As you have seen it, the value of L here is what? 1. So if I want to know the N plus L value of this 2p, it is 3. That is 2 plus 1 is 3. Now to know the N plus L value of this one, here N is 3. S, the L here is 0 because the L value for S is 0. What this S represents is the azimuthal quantum number 0. Okay? Hey, remember all this is you see here are numbers. In order to avoid confusion, that's why we use symbol to represent L, because it will be somehow, if for example now I write 3, 3, 4, it will appear like 33 raised power 4. Whereas this 3 represents shell M, and this 3 represents this, and this 4 represents electron. So that is why scientists have to find spectral terms that will be used to describe these very azimuthal quantum numbers. And we come to the conclusion of this. The spectral meaning of S is sharp. This one is principal, this one is diffuse, this one is fundamental. Okay? So now we look at it very well. The N plus L value for this is 3. that is 3 plus 0. Remember the S is 0. That's 3. For 3D, the L value for D is 2 here. So Yn is 3. So 3 plus 2 is 5. Okay. The N plus L value for 4S is 4 plus 0, which is 4. So this rule called construction principle or Aufbau principle, is the word Aufbau means a German word. Okay, says that you have to arrange electrons into subshells using increasing order of N plus L rule. That is what is commonly known as Aufbau principle or construction building up. So let's define what electronic configuration is. The term electronic configuration can be defined as the process of distributing electrons into the various orbitals, subshells, or shells in the atom. Remember, listen to these 3 words I mentioned. I mentioned orbitals. I mentioned subshells. I also mentioned shells. Okay, these 3 things are completely different. They are not the same, though they are related, but they are not the same. You can decide to write electronic configuration by distributing electrons in orbitals. Acceptable. You can distribute electrons in subshells. Acceptable. You can also distribute in subshells, in shells. Acceptable. But the one that is mostly acceptable, the one that is most convenient is this. Okay. Distributing electrons in orbitals is not, in fact, it is cumbersome because it will be very, very boring for you to do that. Okay, so we normally use this one. That is the distribution electrons in the subshells. Now, the symbol for electronic configuration or notation for electronic configuration is N L raised power X. That is the symbol. That is, remember we're talking about using this one. Now, this NL stands for subshell. Subshell. Then X may stand for number of electrons. Number of electrons occupying the subshell NL. Okay? That is it. Now, also, this N, letter N signifies principal quantum number. Okay? Which represents shell. Because all these things are all combined here. Then the symbol L, small l, represents azimuthal quantum number. Okay? Which also describes subshell. Now, like you know, there are 4 subshells existing in the modern periodic table: the S, the P, the D, and the F. Small letters, please. When you are writing there, you must use small letters. These are the 4 subshells existing in periodic table: S, P, D, and F. So we'll be distributing electrons in them. There are a set of rules you use here. One is that the maximum number of electrons that you can have in the maximum number of electrons that can be accommodated by a subshell is given by this formula: 2L plus 1. 2L plus 1 bracket 2. That is the maximum number of electrons which a subshell can accommodate. This L we are seeing here signifies the azimuthal quantum number of these subshells. Like for example, the azimuthal quantum number of this S subshell is 0, for P is 1, for D is 2, for F is 3. So it means that these symbols you are seeing here represent these figures. S represents 0, P represents 1, D is representing the figure 2, and then F is representing 3. Okay? So for example, now if I want to know the maximum number of electrons a subshell can accommodate, I will put 0 into this equation. If I put 0 into this equation now, 2 times 0 is 0. 0 plus 1 is 1. 1 times 2 is 2. So it means that the maximum number of electrons S subshell can accommodate is 2. So you have this. So that is why you can have 1s1 or 1s2, but you cannot have 1s3 or 1s4. Now, also, if you want to know the maximum number of electrons P subshell can accommodate, you put the LO value of P into this formula, which is LO value of P is 1, and 2 times 1 is 2 plus 1, which is 3. 3 times 2 is what? 6. So it means the maximum number of electrons P subshell can accommodate is what? 6. Okay? And remember, there's a difference between orbital and subshell. A collection of orbitals give subshells. A collection of subshells give a shell. So in every shell you have orbital and subshell. Of course, you know, orbital is the smallest unit, the smallest house electron can be found in the atom. That is, if you define it very well, you say it is the most probable region where electron can be found outside the nucleus. Okay, the most probable, because electron is always in constant motion. So the particular place you are likely to find the electron at a particular instant, at a particular point in time, is the orbital. Okay, it can be anywhere, but that very point you can locate the electron is known as the orbital. So now that is the first rule. Another rule is that you know that in every, the number of orbitals in a shell is given by this formula, n squared. That's the number of orbitals in a shell. So that means that, of course, you have 7 shells in the periodic table. 7 shells: K, L, M, N, O, P, Q. 1, 2, 3, 4, 5, 6, 7. These are the n values of this shell. So which means anywhere you see capital 4, you represent shell n. So there are 7 shells in the periodic table. Okay, these are their principal quantum numbers. So if I want to know the number of orbital now that will be found in M shell, the number of orbital that will found in M shell, I will simply substitute n as 3, which will be 9. So there are 9 orbitals in different orbitals in M shell. If I want to know the number of orbitals that will be found in N, it is 4 raised to 2, which is 16. So you go like that. Now, since another rule there is that about electron configuration is that every orbital accepts a maximum of 2 electrons. No orbital accepts more than 2 electrons. It either accepts 1, 0, or 2. It cannot accept more than 2. So the maximum number of electrons that an orbital can accommodate is 2. Okay? So if I want to know the total number of electrons a shell can accommodate, I will now put these 2. Where these 2 stand for number of electrons that can be accommodated by an orbital. Okay? So which means that if I want to know the number of electrons, the maximum number of electrons M shell can accommodate, it will be 3. That's the number of orbitals in M, which is 9, multiplied by 2, which is 18. Okay? Now, that is it. Now, another important rule guiding electronic configuration, like I've told you, this is the same general. Alright, please, let's now go into practice of writing electronic configuration. Remember, the basic rule you use here in the arrangement is this n plus L rule, okay, which gave rise to the Aufbau principle construction principle. So we have 1s, 2s, 2p, 3s, 3p, okay, 4s, 3d. This is arrangement of subshells in increasing order of n plus L value, energy value. That is this arrangement. So, n, for example, for 1s, n is 1, L is 0. So total, the n plus L value here is 1. For this one is 2, that is 2 plus 0. For this one is 3, which is 2 plus 1. Remember that we have S, P, D, F. This one is 0, this one is 1, this one is 2, this one is 3. These are the L values. Okay? Now, for this, it is 3. For this, it is 4, still 4, and 5. You see, you have to fill electron into subshells using increasing order of N plus L value. Meaning that a subshell with lower N plus L value should take electron first before you give electron to a subshell with higher N plus L value. Okay? So now let's give some examples of